In this video, we are going to discuss about the hybrid pi equivalent circuits of BJT. So, on the completion of this topic, the students will be able to demonstrate the BJT amplifier and the hybrid equivalent and hybrid model. So on low frequencies we can analyze the transistor which we are using in the hybrid H parameters, but for the high frequencies we need some analysis, that is we call it as H parameter model, which is not suitable for this following reasons. So the values of the H parameters are not constant in the case of high frequency, so that it is very necessary for us to analyze the transistor at every frequencies we have to analyze the transistor, and also at the high frequencies the H parameters becomes complex in nature. So due to these reasons only we are going for the modified T model and also hybrid pi models, which is very applicable for the high frequency analysis of the transistors. These models will give a reasonable compromise, that is between the accuracy also and the simplicity, that is to do the high frequency and the thing is hybrid pi common emitter transistor model. So this common emitter circuit, which is not very important in the practical configuration, but it is very useful for the analysis of the hybrid pi model. So you can see the figure of the common emitter configuration. For this model we can be using all parameters which are assumed to be independent of frequencies, but they may vary in the cube. And here CBE, CBC, RBE, RBT, each one has a specified applications. CBE and CBC, which we are calling as diffusion capacitance, and this capacity effect which we are normally forward biased base emitted junction of the transistor, and which we are representing by CBE or CE. So the diffusion capacitance which is connected between this B dash and the E represents, that is excess minority carrier storage in the base, and also the reverse bias PN junction exhibits a capacity effect which we call it as transition capacitance. So this capacity effect is represented as the CBC. And then RBB is nothing but which is the internal node which is physically not accessible by node, which represents the external base terminal, and the RB dash it is the portion of base emitter region which we are connecting in the series and also with the collector junction. So here this established a virtual base connection for junction capacitances. Now RB dash C is that is due to the early effect, this voltage is varying across this collector to the emitter junction causes this depletion region, that is base width modulation. So this change in the effective base width which causes the emitter current to change, so that this feedback effect between the output and the input is taken into account. That's why we are taking this B, we are replacing in terms of B dash. And GM, whenever there is changes in the voltage, that is base voltage across the emitter region, this excess minority carriers will be injected in the base, which is proportional to this base emitter voltage, so that the small signal collector will be shorter to the emitter, and also it is proportional to the base emitter voltage, that we call it as transconductor, and which we are giving as GM is equal to del IC divided by del VC. So you can see the hybrid parameter values for GM, that is the mutual conductance, that value is 50 milliamps per volt, and RBB dash, that is base spreading resistance 100 ohm, RB dash E resistance between the B dash and E, conductance between B dash and E, it is 1 kilo ohm and 1 mid. Then RB dash E or GB dash E, resistance of the reverse biased PN junction between the base and the collector, conductance of the reverse biased PN junction between the base and the collector, which we can which the value is 0.25 into 10 power minus 6 ohm. Then RC or GCE, that is output resistance between C and T, conductance between C and T, that is value is 80 kilo ohm and 12.5 into 10 power minus 6 ohm. Then CE, that is junction capacitance between B and C, CC junction capacitance between base and the collector, which value is 100 picofarad and 3 picofarad. And the transistor capacitance value diagram is given here. And here we are calculating the, that is GM is equal to dou IC divided by dou VBE, and the collector current in the active region we can write it as, that is minority current plus majority current, dou IC is equal to alpha into dou IC. We can substitute the value of dou IC, so that you will be getting that GM is equal to alpha into dou IE divided by dou VB dash E, that is equal to V is equal to VB dash E. And the emitter diode resistance which is given as R is equal to dou VB divided by dou IE, that is substituting these values we will be getting, that is 1 by R is equal to dou VE divided by dou IE. So here you can find out the input conductance of the hybrid model of the CE at low frequency, and also H parameter model of for C conversion low frequencies. HF is equal to IC divided by IB. IC divided by IB is nothing but GM into VB dash, which is VB dash we can write as I into R. So that is GM into IB into RB dash. That is, you can take this IB down, that is GM into RB dash. Substituting those values, you will be getting GM is equal to IC divided by V. Thank you.